Alright, so what we want to get started with today is start working on solving some circuits, doing circuit analysis. We'll do some of that today, and then some more complicated stuff on Wednesday. So here is a traditional circuit, the way that we draw them, the way you'll see them, you have seen them in the textbook in this chapter. In real life, they would look more like that, the way batteries look and resistors actually look like that with color codes on them and whatnot. But when we draw them for analysis, that's the schematic version. And so we're going to start looking at those more frequently. And so in this circuit, just to be clear, here's our battery over here, and it's in series with that resistor. And then we break off into these parallel branches before coming back to the battery. So current will flow, electrons will flow one way around the circuit, and then conventional current is the opposite of that, and we've gone over why we have this weird convention. So what we need to be able to do is deal with the circuit and how to analyze its properties. So for resistance, when resistors are in parallel, okay, so here we could call this R1, we could call this R2, and we'll call this R3. So big R for resistance. We just give them some label, A, B, C, 1, 2, 3, whatever floats our boat. But R for resistance, because we're dealing with Ohm's law, which says voltage is current times resistance. That's generally true for all circuits. And technically speaking, Ohm's law really isn't a law because it falls apart when the resistor gets too hot. It's not always true, mostly true, but we ended up calling it a law anyways. So parallel resistance. I think the other day we showed that 1 over the total resistance would be 1 over the first resistor in parallel plus the next resistor in parallel, etc. All right? And so for a 2-resistor circuit, you're going to get total resistance is going to be the product of the 2 resistors over their sum. And we've already done this math before for series capacitors. Capacitance adds arithmetically when they're parallel, but it adds this way when capacitors are in series, and the opposite is true for resistors. So the series and parallel formulas for capacitors and resistors are opposite of each other. Parallel resistors and series capacitors are the 1 over form, and series resistors and parallel capacitors are just simply add them up arithmetically. All right? So what we're going to need to do is, before we can figure out what the current in the circuit is, because we know what the voltage is, there's one power supply, it's a 9-volt power supply. We need to figure out what would be the equivalent resistor for this parallel network. We need to reduce, if you will, that parallel network down to a single resistor. What would be an equivalent resistor for this parallel branch? And then once we know what that is, we could add that to the one that it's in series with, and we would have a total resistance for the circuit, etc., etc. And so why don't you take a minute and figure out what would be the total resistance for this parallel branch. I guess to be consistent with our notation, in this case I need to change these subscripts. These should be all 2s and 3s instead of 1s and 2s. I was just being general. So let's be careful since 2 and 3 are in parallel. So if we do this math, we're basically going to have 20 times 10 over 20 plus 10, and that's roughly 6.7. Now in the simulation, we can't do 6.7. It'll let us do 0.5 intervals. All right, so we'll have we'll get close when we run the simulation to the right answer. So now what that means for us is this circuit. Which way was that battery? The other one I think was 10. If it was just comprised of one resistor. So this is going to be the current that's going to come out and go, if it's flowing in that direction, is going to go through that resistor. And then it's going to break up in this parallel branch. But what we're going to see is that there's this is the, I guess, the size of the hill, if you want to think about the electric potential. And this resistor is going to eat up some of that electric potential and leave the rest to go on this branch right here. So in order to figure out what potential drop is across that resistor, I have to know what current's going through that resistor. And it really wouldn't matter whether the current was flowing this way or that way in the circuit. When it goes through that resistor, it's all the current. It's the total current in the circuit. Okay? It has to be either, if it's coming out of that end of the battery, it's the first thing to experience the total current of the battery. And if it's coming out of that parallel branch, well, the parallel branch was fed by the total current, split up, came back together, still the total current. It has to be that way. All right? So now let's erase all of this. You know, so we can take our 9-volt battery, and we had this would be, we can call this R23 because it was the compilation of resistors 2 and 3 in there. And this ended up being 6.7 ohms to start with. And series resistance is just going to be the total resistance, which we could call R123, will be R1 plus R23. And so that's easy, 16.7 ohms. That's that omega symbol, Greek omega, sort of like an upside down horseshoe, or whichever direction a horseshoe's straight up is debatable, I guess. And so that means with Ohm's law, the general version here, and the assumption with Ohm's law is that for whatever you're dealing with, it's the total voltage across that and the total resistance. Okay? And in a series circuit, there is only one current. So we could, given that we know the voltage of 9 volts, we could compute what the current's going to be in this circuit. .5389 and some change amps. And we use a capital letter A for amps. Now, since this is, we typically don't write that much decimal precision, and in fact, we have no good reason to write that much decimal precision given the significant digits we're dealing with. But, you know, your calculator spit out a big old long decimal number. And what I want to do is put it in scientific notation and in the kind of scientific notation that makes sense for circuit analysis. I could write this as 539 times 10 to the minus 3 amps. Okay, so because if I move that over, multiply that by 1,000, that 0.5389, I would get 539, but then I have to offset that with the multiplier. Okay, so this is really just, if I take 0.5389 times 10 to the 3 times 10 to the minus 3, okay, so then that boils down into the 539, okay, so just keeping everything balanced. And so that means my current is essentially what we would call 539 milliamps. Okay, because 10 to the minus 3 is a milli, 1/1000. So, 600 milliamps is 0.6 of an amp. 900 milliamps is 0.9 of a entire amp. Okay, and 1,000 milliamps would be 1 ampere. Okay, and 1 ampere is already in the deadly zone. Estimates vary, but deadly amperage, some folks will say, is as low as half this level. I don't think that's correct, but we do know 1 amp is definitely deadly. Most people do not recover from a 1 amp experience with that. So now we know what the current in this circuit. So we can see 0.54 amps. What does our 0.5389 whatever boil down to? 0.54. So this one will only give us 2 decimal precision. So we did the numbers right. We can all keep our jobs. All right. And so now it's trying to figure out what is going to be the voltage drop, because we need to figure out what the current's going to be in these other 2 resistors. All right. So what we can do is figure out what the voltage. So remember, this was R1. That was R2, and that was R3. Okay. So now that we know that there's 0.54 amps going through a 10 ohm resistor, we can compute voltage 1. And that's going to be total current times resistance 1. So this is just simple math here. We're going to, since it's 10, it's a nice number to work with, 0.54 times 10 is going to give us 5.4. So the voltage 1 should be 5.4 volts. So let's see. If that's correct. 5.4 volts. So now we know that the voltage that's left over in the circuit is just going to be the difference between 9 and 5.4. Why is that? Conservation of energy. And the reason why I'm stressing this is that I don't think we're going to get to it today, but on Wednesday we will need to actually apply the Kirchhoff laws, the node and voltage laws that we had in lecture, and those are all about conserving energy. You always have to conserve energy, and we're just taking a simple path at the moment. So our math checks out, yay. So that means that over here, this parallel branch, the voltage drop here, all right, has to be equal to the 9 minus 5.4. All right, or that's going to be 3.6, right? So we know that there's 3.6 volts on this parallel branch. Now, the thing to, and we already covered this once before when we were dealing with capacitors about how the how voltage drops work. And so we can just kind of verify, okay, so 3.6 volts, just like I said. We dealt with this when we dealt with capacitors. So requiring that, so that means that each one of these resistors in parallel is experiencing a 3.6 volt drop. Okay, if we wanted to, we could actually put these leads on the actual resistor and see that it's 3.6. And that's because this point up here, the branching, the nodes that define the parallel branch, electrically they're identical to those points. So that those forks in the road, those long wires, doesn't really matter that they're long wires. It's technically one point as far as electricity is concerned. They're electrically the same. But often we need to spread devices out with wires. Like these lights need to be spaced. Like if I just ran them all together, that wouldn't suit the design. Need them spread out so they light up the room better. All right. So now we've verified that. So that means that the current can be computed in these. And so V2 would be, well, here's the thing is we have current coming in here, so we can call this current 1. We can call that current 2. We want to switch. Let me switch to conventional just for grins. And we could call this I3. All right. So switching to the conventional current flow, which is the opposite of the electrons flowing. All right. So the voltage across resistor 2, this right here, would be current 2 times resistance 2. Well, I know voltage 2, it's 3.6. The resistor is a 10 ohm resistor. What I don't know is what the current value is. Well, that's just going to be the ratio of them two things. And so voltage is 3.6, resistance is 10. Looks to me like this will be 0.36 amps. So I can come over here and swipe this fancy current meter and verify that yes, current through that branch is 0.36, which means that the difference between 0.54 and 0.36 is what the other branch has to hold. All right, so we could put 0.18 there, but we could also compute it. So since that's the goal, generally speaking, here is I3 will have the same structure as I2, except it'll be the voltage 3 divided by resistance 3, and the voltage was 3.6, resistance is 20. So guess what? It should be half of the 0.36 or the 0.18. Okay, and that should have been obvious if one leg is getting a certain number of amps going through it and the other leg in parallel is double the resistance, then it should have the flow. So that's why I picked these numbers, just for that simplicity. At least they didn't make sense going in, they should make sense coming out. And so now we've computed all of the currents in the circuit, the total current and how it splits up, and we were able to determine the voltages. We computed one voltage, which told us what the other two had to be. So we didn't compute the other voltages, but we determined what they would be by the way the laws work. And so there's our first circuit analysis, if you will, for the course. So now what we need to do is change it and see if you guys can figure out what it is. Let's add a new screen here. All right, so what I want you to do is draw that circuit, choose some appropriate labels. Let's go ahead and, so we're all on the same page, we'll call this resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5. And we'll just leave all of those ohms at 10. Let's do this though. Let's make things nice, and let's turn this battery into a 10-volt battery. So what I want you to do is solve that circuit. And so when we say solve a circuit, that means find out what is the current and voltage through each device. Now, you don't have to put in the current values, okay? I'm going to leave that open for the moment. Or I mean, don't put in the current boxes. Just leave those out, if you will. So I'll tell you what, I'll go ahead and do that. So this would be our circuit. Drawn the way that you typically see them drawn. And so find out what the voltage and current across each of the 5 resistors is. That is what it means to solve the circuit. So I'm going to pause this here and give you a chance to work on that for a little bit. This, well, actually, let's be careful about this triple branch parallel-wise, okay? So this one, I'm going to bring up a clean page. This network boils down to a 3.3, so total resistance will be R1 plus R234 plus R5. And that means total resistance will be 10 plus 3.3 plus 10, or 23.3 ohms. That'll be the total resistance in the circuit. And what that means is that total current is going to be voltage over total resistance, and that means I'm going to keep that going, 10 over 23.3, and that should just be 2.3 amps. I'm sorry, that's flipping that over in my head. So we should get 0.43 amps out of that. So let's see what happens here. Oops. Ah, my circuit goes away. Well, so much for this thing cooperating with us. I had high hopes for embedding the circuit um, thing here. So 1 over R2, 3, 4. So meaning the combined resistance of resistors 2, 3, and 4 would be 1 over R2 plus 1 over R3 plus 1 over R4. Did you do that? That would be the setup for that. Which means, in order to solve this, I need a common denominator, which means I need to multiply this one by R3 and R4 top and bottom, this one by R2 and R4 top and bottom, and this one by R2, R3 top and bottom. All right? So 1 over R2, 3, 4 would be R3, R4 over R2, let's see, save the denominator for last, or stick it here in the middle, plus R2, R4 plus R2, R3. So it's still sort of a product and sum game, and you're always going to have the product of all of them divided by the sum, but it's when it's more than 2 resistors, it's going to be the sum of all the product combinations. That will always work out to be. And if you have 3 resistors, then there's 3 combinations of multiplying them. So this means R2, 3, 4, if I flip all of this over, will be R2, R3, R4 over the sum of R3, R4 plus R2, R4 plus R2, R3, which will be 1,000 over, well, each one of these is 100, right? Okay, so, because it's all tens, 10 times 10 is 100, so 100 plus 100 plus 100, so R2, 3, 4 will be 1,000 divided by 300, which will be 3.3 ohms. Now this, one of the things to remember, so you don't make the mistake, which I think we made due to a lack of clarity, which is caused by a lack of caffeine. I'm not far enough through this jug. Every time, it doesn't matter how big or small the resistors in a parallel network are, the total resistance of the parallel branch will never be bigger than the smallest resistor. And so what we said would be 33.3. That's impossible because the smallest resistor is 10. But 3.3 is definitely less than the smallest resistor. So in here. So that was the new layer, I guess. Is how this breaks out with that third resistor. But what should always work out, and it wouldn't matter how many terms I added, how many I had in parallel, it would always be the product of all the resistors divided by the sum of something. And when it's more than 2 resistors, it will be all the product pairs that are possible. That pattern won't change. But the difference is if I added a 4th term, then it's going to be product triplets. So it's always going to be the sum of the product of one less than the total number in the, so you could skip the actual common denominatoring of it and just apply that rule. We're not going to do humongous parallel branch networks, more than 3 anyways. At least I don't plan on it. So let's build this puppy again. Sorry for the so as I recall, we had one resistor in series with 3 in parallel, all the default values, put those together, came out of here, another resistor, that battery went bigger, 10 volts, there we go. So, yay, our computation of 0.43 amps works out. And so now we need to figure out what will be the voltage drop across that resistor. So it's a 10 ohm resistor with 0.43 amps going through it. So what's the voltage drop across these top and bottom resistors? Not all at once. So this was our R1, R2, R3, R4, R5. So current one's going to equal voltage I'm sorry, I need voltage here, not voltage 1 will be current times resistance 1, and that should just be 4.3 volts. This one's going to be 4.3 volts as well. So almost all of the voltage is eaten up by the resistors that are not part of the parallel branch. So what's the voltage drop on this parallel piece of the circuit? You have 8.6 eaten up on both ends of the parallel branch. That leaves behind .4 volts. So we can verify that. So 1.43 volts here. Those points are the same, if you will. So apparently this is, let's see, oops, that's not what I want. So basically, it's doing 2 decimal places, 4.29, same as 4.3, all right? So we'll go with our numbers. here. So that means we can figure out what the current going through any one of these resistors is, and since they all have the same voltage and they all have the same resistance, then I2 equals I3 equals I4, which is going to equal this 1.4 volts divided by 10 ohms. And that will be just 0.14 amps, which we can verify. There we go. 0.14 amps. Each one of those legs has 0.14 amps going through it, which should make some sense, because what's 3 times 0.14? Should add up to basically 0.42, and if it had all the decimal precision that the voltage meter has, or that we had computed, then we would get that 0.43 amps back again. Okay, so that's a slightly more, we added 2 resistors, an extra series one and an extra parallel one, to do the math that we had back. So interesting. So that one, it kept the circuit, probably because I clicked out of it. Interesting. All right, I'm going to